So we have our car, and its mass is 500 kilograms. The engine is going to supply a force of 1,500 newtons, and we want to determine what the acceleration this car is going to experience is. So all I need to do to find the acceleration, and I'm going to drop the vector symbols, mainly because if my acceleration is in the direction that I'm moving, then everything is positive, and so the direction is implied. And the magnitudes can just be calculated from this equation. And so all I do is take 1,500 newtons and divide that by the 500 kilograms in the mass, or of the mass rather, and I can write this as kilograms times meters per second squared, just so you can see how the units are going to work, right? And so the acceleration the object is going to experience, let me write that a little bit better, the acceleration is going to be 1,500 divided by 500. And so 1,500 divided by 500 is going to be 3. And my kilograms are going to cancel with my kilograms, and so that's going to be meters per second squared. So the mass of this car, 500 kilograms, and the force being 1,500 are going to act together to produce the acceleration of 3 meters per second squared. If I had a larger mass, then my acceleration would be smaller. If I had a smaller mass, then my acceleration would be larger. And that harkens back to the whole inertia idea that we were talking about. Now let's do an example of centripetal acceleration, and let's let the same car be moving around a circular track, all right? And let's let the radius of the track be 100 meters, right? And we'll let the speed of the car be 20 meters per second. And I want to know what the centripetal acceleration is, and B, if we use the same car so that our mass is the same, let's let the mass equal 500 kilograms. If the mass equals 500 kilograms, what is the centripetal force as well? All right, so I want to know what the centripetal acceleration and the centripetal force is as well under these conditions. All right, so let's start with the centripetal acceleration. So again, centripetal acceleration is equal to v squared over r, and v is 20 meters per second. And we square that, and we divide that by the 100 meters. And this is going to give us 400 meters squared over seconds squared divided by 100 meters. And this gives us my meters on the bottom cancel with one of my meters up top, which gives me meters per second squared, which are the units on acceleration. I didn't prove the units on acceleration earlier, on centripetal acceleration earlier, to show that they were consistent with acceleration, but they are. And so 400 divided by 100 is just 4 meters per second squared. And that's the centripetal acceleration pulling the car toward the center of curvature. All right. Now, in the next section, next chapter, we will find what that force is. All right. But for now, we will leave it that there is a force causing the car to accelerate toward the center of the circle. All right. Now, if I know what the centripetal acceleration is, what is the centripetal force? Okay, what is the centripetal force? Well, F equals ma. And so that means that the centripetal force just equals the mass times the centripetal acceleration. And so ma becomes mv squared over r. And this is the equation for centripetal force. All right. F sub c equals mv squared over r. Now we've already calculated v squared over r, it was 4. So all I now have to do is take my 4 meters per second squared and multiply that by my 500 kilograms, and I get 2,000 newtons. All right. So the centripetal force on my car is going to be 2,000 newtons, which we found was more than what the engine itself was supplying when the car was accelerating at 3 meters per second squared. All right. Now, in the next video, we're going to explore Newton's third law, and you're probably more familiar with it than you realize, but we'll dig into it a little bit deeper.